Topic 18 focuses on chemical equilibrium and how we can quantify it. First, we recap the ionisation of water, which we came across in topic 13 in our discussion of acids and bases. We look at quantifying reactions that are reversible and calculating a reaction quotient, Q. This gives us a snapshot of the reaction at a particular instant. A special case, called equilibrium, is characterised by an equilibrium constant, K, and occurs when the speed of the forward reaction exactly matches that of the reverse reaction. The value of K is unique for each equilibrium system and is a characteristic of that chemical system in much the same way that a melting point is a characteristic of a solid. We look at what happens to an equilibrium when we change the conditions. And finally, we find that the presence of a solid in an equilibrium has perhaps a surprising role when calculating K. We saw in topic 13 that water can split up or ionize to form H plus and OH minus. The reaction is reversible, and H plus and OH minus can recombine to form a water molecule. Both the forward and the reverse reactions occur at the same time, and when the speed of both reactions is the same, there will be no overall change in the concentration of the species present. The reactions do not stop occurring, it's just that the water molecules are breaking into the ions at exactly the same rate as the ions are combining to reform the water molecules. In an equilibrium, all of the different components of the reaction are present. In this case, H2O, H plus, and OH minus, but not at the same concentration. Either the reactants or products dominate. In this example, careful measurement of pure water shows there are approximately 1 H plus and 1 OH minus ion for every 500 million water molecules. Sometimes an equilibrium situation has been likened to a seesaw in balance, but this is a static balance and does not adequately describe a chemical equilibrium in which the forward and reverse reactions are still occurring, but now do so at the same rate. I think of an equilibrium as being rather like two buckets of liquid connected by a pipe. At the start, only one bucket contains liquid, and when the tap is open, there is a flow into the empty bucket. I could also have started the process by filling the second bucket, and then there would be flow into the first container. After a while, the levels in the two buckets become equal, and while liquid can still flow through the connecting pipe, it does so in both directions, so there is no overall change. However, this analogy needs to be a little bit more sophisticated to describe a chemical equilibrium, and it is extremely unlikely that you end up with equal amounts of products as reactants. This is because different compounds have different energy content, and consequently there is a dominance of one side of the equilibrium over the other. I could represent this as buckets at different heights. Opening the tap, the flow occurs, and at equilibrium, the surface of fluid in each bucket is the same, even though the lower bucket contains a greater volume of liquid. Once again, liquid can flow between the buckets in both directions, and when it does this with the same rate, there is no overall change in volume of liquid in either bucket. Every chemical reaction is unique. A way to quantify the progress of a reaction is to calculate a reaction quotient, given the symbol Q. The reaction quotient describes, in numerical terms, the mixture of reactants and products present at any one instant that the concentrations of the reaction components are measured. There needs to be a measurable amount of all reaction components to obtain a meaningful value of Q. In the simplest case of a single reactant and a single product reacting in a 1-to-1 ratio, or stoichiometry, A to B, the value of Q is calculated by dividing the concentration of the product by that of the reactant. A more general case is when there are stoichiometric multipliers present in a balanced chemical equation, such as N2O4 reacting to form 2 lots of NO2. Here, the stoichiometric multiplier, 2 in the case of nitrogen dioxide, is the power to which the concentration of NO2 is raised in calculating the value of the reaction quotient. In more complicated cases, a similar pattern is followed. That is, Q is calculated from the multiplication of the product concentrations, each raised to a power represented by their stoichiometric coefficient, divided by the multiplication of the reactant concentrations, also each raised to the power represented by their stoichiometric coefficient. Let's look at a couple of examples of calculating Q. Firstly, it is important to write which chemical equation Q refers to. For example, sulfur dioxide reacts with oxygen to form sulfur trioxide. We can write an equation for this reaction and an expression for the reaction quotient associated with this equation. An equally valid chemical equation for this reaction has the same reaction ratios of sulfur dioxide, oxygen, and sulfur trioxide, but different coefficients in the equation, and hence a slightly different expression for Q. But does this matter? Putting in values of the concentrations into the two equations for Q gives different answers. So yes, it is essential to write the chemical equation alongside the reaction quotient. In all reversible reactions, a point comes where there is no net change in concentrations. This is called the equilibrium point. When equilibrium is established, it can be described by a constant K. The forward and the reverse reactions continue, but they occur at the same rate as one another. K is calculated in a similar way to Q and is a characteristic of the reaction. In the same way that the melting point is a characteristic of a solid. To extend this analogy, in the same way that the solid may be at many different temperatures but has a single melting point, so a chemical system may have many different values of Q but only a single value of K. The value of K must always be linked to the exact equation to which it refers. The temperature at which the equilibrium constant is measured must always also be stated, as K is temperature dependent. We will see the variation of K with temperature in a moment. For the value of K, we can immediately get a feel for the position of the equilibrium. If K is greater than 1, then the top of the equilibrium expression must be greater than the value of the denominator. As the top of the equilibrium expression is derived from the concentration of the products, then products must predominate. Conversely, if K is less than 1, the denominator, or the bottom part of the expression, is greater than the numerator, or top part, and this is associated with a predominance of the reactants. Note that while K may be very small, it can be never negative, or less than 0, as concentrations always have a positive value, however small they are. For any particular equilibrium, there is a unique value for K, while there is an infinite number of possible values of Q, depending on when the measurements were taken before the system reached equilibrium. So we might ask the question, why bother with calculating Q? Well, a comparison of Q and K will tell us in which direction the reaction is going and how close it is to achieving equilibrium. For example, if we find that calculation shows a Q for a particular system, SO2 reacting with O2 to give SO3, has a value of 0.13, and from data we find that the value for K for this equilibrium is approximately 8 times 10 to the 4, then seeing that Q is less than K, we can deduce that the reaction proceeds to generate more product and will continue to do this until equilibrium is reached. So if Q is less than K, the system moves to generate more product, whereas if Q is measured at an instant when it is greater than K, then the reverse reaction dominates and the system moves to generate more reactants until equilibrium is established. I now want to look at a complex calculation. When we're looking at stoichiometry back in topic 9, we saw, for example, how we could calculate the amount of product we expected for a given quantity of starting materials. This works well for reactions that only proceed in one direction to the product. But what happens when an equilibrium situation in which we end up with a balance of reactants and products occurs? Take the equilibrium between hydrogen, iodine, and hydrogen iodide as an example. I want to start with 1 molar concentrations of both hydrogen and iodine and calculate the concentration of all 3 gases at equilibrium. I like to set this up as a table of concentrations. We're given the initial concentrations of the reactants. We don't know how much of these reactants will be used up, so let's call the change in concentration Z. From the stoichiometry of the equation, we get twice as much product generated as reactant used. So we can arrive at the equilibrium concentrations in terms of Z. For hydrogen, this is the initial 1 molar minus the change, Z. For iodine, it's also 1 molar minus Z. For the amount of HI that we generate, it is 2Z. Substituting these values into the equilibrium expression results in a quadratic equation. Solving a quadratic equation gives 2 answers, one correct, one incorrect. In this case, Z is solved mathematically to give either 0.63 molar or 1.54 molar. Looking back at our table, the correct value must be 0.63, as taking the other figure would give a negative concentration for both of the reactants at equilibrium, which is impossible. And hence we have calculated our final concentrations of all the species present. One of the characteristics of a reversible reaction is that it will always move towards its equilibrium position at a given temperature. And the value will always be the same, irrespective of the starting concentrations of the components. Now let's look at a situation where a reaction, already at equilibrium, is perturbed. For example, if more starting material is added, here the reaction will move to remove some of the added starting material and generate some more product as a consequence. the graph attempts to visualize the system of an equilibrium between A and B. If we start at equilibrium, the concentrations of A and B are steady. If we now add some more A, the concentration of A jumps up and the equilibrium is perturbed. Q is now less than K, and we have increased the size of the denominator in the reaction quotient expression. The system will react to counteract the change by moving to the product side. The concentration of A is reduced to remove part of what has been added. Consequently, the concentration of B increases, and the value of Q increases towards that of K. After a time, equilibrium is re-established, and while the concentrations of both A and B are greater than the initial situation, the value of K is identical. Now look at the situation in which one component is removed. The system will adjust to generate a little more of that component, though it can never fully make up for the loss. In this example, we start with the system at equilibrium, then remove some of the product. This results in a sudden drop in the concentration of B. As the system moves towards equilibrium, some of A reacts to form B to replace part of what is lost. At the moment at which we remove B, the top part, the numerator of the reaction quotient expression, gets smaller, and so once again Q is less than K. When the new equilibrium is established, there is slightly less of both components than before the perturbation, but the relative ratio of them remains the same, and Q is the same value as before. In a final example of this series, imagine that A and B are both gases at equilibrium in a sealed syringe-like reaction vessel. If we reduce the size of the reaction vessel, the pressure will increase. The concentrations of all components present will also increase, as they're now contained in a smaller volume. Recall from topic 15 that the pressure of a gas is proportional to the number of moles of gas present. In this example, the reaction stoichiometry shows there are twice the number of moles of product B as reactant A. When the pressure is increased, the reaction adjusts to reduce the total number of moles of material present, and hence reduce some of the added pressure. It does this by shifting the reaction to the left-hand side. Thinking about the value of the reaction quotient when the pressure is increased, while the concentration of both A and B increases, as Q is calculated from the square of the product concentration in the numerator, but only the concentration of reactant in the denominator, the value of Q increases. When Q is greater than K, the reaction shifts towards the reactant side until the value of Q is equal to that of K and equilibrium is re-established. I have repeated that it is important always to indicate the temperature as well as the chemical equation when indicating a value for the equilibrium constant for a particular chemical reaction. This is because K varies with temperature. Recall topic 16 on energy, in which reactions may be classified as either endothermic, in which heat is absorbed in the reaction, delta H is positive, or exothermic, in which heat is generated in a reaction, delta H is negative. This may be illustrated by examining data for a couple of different equilibrium reactions. In the first case, an endothermic reaction, and in the second case, it's an exothermic reaction. Note that changing the temperature will also affect the rate at which the forward and reverse reactions will occur, But unlike the equilibrium situation, in which the species favoured depends on delta H, the rate or speed of the reaction is always increased as the temperature is increased. The presence of a catalyst in any chemical reaction will increase the rate of reaction, but it does not change the amount of product obtained. Similarly, if a catalyst is present in an equilibrium system, it will speed up the rate at which equilibrium is achieved, but it will not change the concentration of any of the species present at equilibrium or the value of K for that equilibrium. Now to solids. Understanding the role of a solid in an equilibrium is a little bit more tricky. Imagine you have a block of wood and that you measure the density to be, let's say, 0.7 grams per cubic centimetre. Now, if you cut the wood into two pieces, each piece will still have that density of 0.7 grams per cubic metre, even though the amount of wood present in each piece is smaller. Density is directly analogous to the concentration within a solid. As a system moves towards equilibrium, the density and concentration of a solid does not change, even if some of it is used up or added to, unlike the concentration of species in dissolved solution. Consequently, solids do not appear in the equilibrium expression K. To recap, finally, for a reversible chemical reaction, equilibrium is reached when the rate of the forward reaction equals that of the reverse reaction. This requires there to be some amount of all chemical species present. Both forward and reverse reaction continue happening, but there is no net change in the balance of reactants and products. This balance is quantified by the equilibrium constant. Leading up to equilibrium, the rate of the forward and reverse reactions differ, so there's a net shift in the concentration of the species present. At the moment of measurement, this may be characterized by the calculation of the reaction quotient. Note that Q and K are ratios and not fixed to specific concentrations. We find that perturbation of the equilibrium will cause a change by the system to re-establish the equilibrium. If we add a component or remove a component, then the equilibrium will shift to counteract this change. The equilibrium constant K will not change. Only in the case when we change the temperature of a reacting system will the equilibrium change. Thank you.